Good morning, everybody.
Morning.
And
Hello. So let me ping all the people that the TSC starts. Okay, so how many are we from the TSC? 1, 2, 3, 4, 5. That's good. Um, so welcome to the TSC meeting. Let me find my window. Here we go. Welcome to the TSC meeting. If you're here for the first time, this is a meeting of the Technical Steering Committee of the Hiero project at the Linux Foundation Decentralized Trust. We're an open source project under the Linux Foundation, and in the TSC meetings, the Technical Steering Committee is discussing several topics, like, for example, today we will have a look at some improvement proposals for the Hiero network. And like any other meeting we do, this is a public meeting, which means everybody is welcome to join our meetings, not only the TSC meeting, but every meeting we do under the Hiero project. We have a public calendar. You can find links to it on our webpage or in the meeting minutes, as you can see. So today, this as an example is the first meeting in a row of 3. So I'm located in Germany. That is why my time might be totally different to your time, but the calendar is working on your time zone. So feel free to join any of those meetings. If you missed meetings, the meetings will be recorded, like this meeting is. And if you go in the calendar back in time, like 1 week, you have a link to the recording of the meeting. So if you miss a meeting because you're on vacation or whatever, you can do a rewatch of it. And since it's public, one important thing is that the meeting happens under the code of conduct of the Linux Foundation, which means you please ask questions please contribute to those meetings, but do it in a friendly manner, and then we're all good. And next to the code of conduct, the meeting happens under the antitrust policies of the Linux Foundation. Okay, so let's start with the meeting. We have a quite interesting agenda today. We have two HIPs on our timeline we would like to have a look at. I see Mark is here. Mark, is it again you who will present those HIPs, or is it somebody else?
I
Yeah,
will present the smart contract throttling HIP at least. Mark, I don't know if you wanted to do the generalized schedule contract call, or I can do that one too.
Yeah, I wasn't involved with that one, so if you could do it, it'd be great. Thank you.
Okay, sounds good.
Okay. Then maybe we just directly start with the smart contract throttling topic, Richard, and I will stop sharing and you can share your screen.
All right, sounds good. So we're not intending to, I think this is the first time that we've brought both of these to the TSC. So I do not intend us to vote on it today in any event because you need some time to read through this and look at these things. I'm going to start with just a quick look at the HIP itself, and then I have a diagram that I created where I can kind of explain more precisely what this precise smart contract throttling talks about. So this is the HIP. There have been no comments on it, so I'm not sure if people have had a chance to look at it or not. It's reasonable length. It's not terribly long. The whole point on this is um, to increase the amount of gas per second that we're able to execute um, to something closer to what the system is actually able to achieve. So the best way to describe this is that gas is a very crude method for measuring two things. One is the amount of computation that a thing takes. And the second thing is how much you had to pay for it. And I say that it's crude because depending, there are several aspects to payment for things in an EVM. One is, let's say you have an add opcode, or you have a multiply opcode, or you have a divide opcode. These are pure computation opcodes, and they have some amount of gas that's associated with them. And the purpose for that gas is to represent the amount of computation that was done by those things. But they're, like I say, they're crude. They're not ultra precise, and which is okay. Having a crude metric would be okay if every opcode was consistently priced based on its relative cost to each other. But it's not. Some things are super low, like 3 gas to do an add, and other things are low but should be higher, like say doing a kakac hash on the node. So the way that you determine whether sort of what the real cost of the gas is that you create a smart contract. And in that smart contract, you execute the same opcode over and over and over again. And then you measure the amount of wall clock time that it took to execute that contract. And then you do that a whole lot of times to work out all of the sort of small variances. And you can figure out what the gas per second is for that opcode. So like, let's say, for example, that I do the add opcode, and let's say that that add opcode is 3 gas, but when I measure it at about 20 nanoseconds per opcode invocation. So I know that if I've got 20 nanoseconds, then and there's a billion of those per second. So if we've got a billion, let's see, a couple more zeros, divided by 20, gosh, that's like 50 million. 50 million of those per second. And of course, it's 3 gas. So that gets me 150 million gas per second. That's what I could do with an add opcode. But then I take another opcode. Let's say that it's the S load. This is the one that loads state from, loads state into the EVM. That opcode, if you're doing like a cold load, is something on the order of 20,000 gas. So let's say that I can do that in, I don't know, 100 nanoseconds. All right. So if I go back to, a billion nanoseconds per second, and I divide that by, what did I say? 100 nanoseconds? Sure. I divide that by 100 nanoseconds, that's 10 million. Okay, I can do 10 million S loads per second, let's say. And if each one of those is 20,000 gas, then I multiply that by 20,000, and wow, I just had 200 billion gas per second. So you can see how if you're measuring based on gas per second, sometimes you get a smaller number, sometimes you get a larger number, and it totally depends on what is the actual performance for the thing times the amount of gas per second that it is. That tells you your maximum gas per second. Unfortunately, we have to set the gas throttle on our system low enough so that the worst case scenario is safe. So maybe I can do 150 or 200 or 300 million gas per second for a standard contract, but I have to limit it to 15 million gas per second because a bad guy could come along and write a contract that just did the worst opcode, which is Kachak hashing. He could just do that hash code or that opcode over and over and over again, that precompile over and over and over again. And if he did so, then the network would only be able to do, maybe 30 or 40 million gas per second. And since our throttle is at, would be at like 200 million, they could abuse the network and make it unavailable to anybody. They could do a denial of service. So because of that, we have to choose a gas per second throttle that is low enough that, uh, to preserve the network, even though we have a ton more capacity. The same is true for our TPS numbers because we have to figure, okay, the minimum gas per contract multiplied by the TPS, what's our safety margin and so forth. Now, we wanted to answer the question. We wanted to answer two questions. One question was, okay, in our code base today, what's the actual maximum TPS that we could fire up smart contracts with? And it turns out it's over 10K TPS. I mean, we have the throttle set at 300 TPS on Hedera, but it could be higher. Now it doesn't do us any good to make it higher because 15 million gas. If you took 15 million gas, by the way, the term intrinsic gas price is the amount of gas that the minimum gas that any contract call uses just to start the contract up. And that's I don't remember the numbers, 20,000 or 21,000, something like that. So I'll just say 20,000 is like 750. So at 15 million gas per second, literally the highest that we could make the thing was 750. But we always have a safety margin in play. Plus, we wanted to preserve space on the machine for being able to do non-contract calls, so contracts didn't consume all of the available resources. So that's why we're at 300. We took 750, which was the maximum that you could do, divide it by 2. That's kind of a safe number. So it's 300 is what it's set to. But if we were to just say, forget about the gas per second throttle, if we just took off the throttles entirely, how quickly, how much time does it really take to start up the EVM? Turns out not very much time at all. And we could easily do 10,000 per second. So that's an interesting number. If you're trying to optimize the amount of utility for your system, knowing that you can get up to those sorts of numbers, you go, okay, that's interesting. It's not useful because of our gas throttle, but it's interesting. The second thing we wanted to do is we wanted to say, okay, if you're going to try to benchmark what the performance of your system is from an EVM perspective, everything matters in terms of how what type of contract are you executing? Because just like I said, there are certain opcodes that you execute that will get you hundreds of millions of gas per second. Certain opcodes you can execute that will get you tens of millions of gas per second. We even have opcodes that we've executed that got us over 1 billion gas per second. But the question is, what contract are we measuring to see what we can really do? So what we did was we talked to the HeliSwap team and said, hey, you guys have a Uniswap port. Let's run that thing on our network and just see what our throughput is. And we have roughly doing real swaps. Okay, so the point was we're not messing around. We're not picking some synthetic benchmark. We're going to take Uniswap and we're going to just say, which both Saucer Swap and HeliSwap are ports of Uniswap. V2, and we'll just say, you know what, I am going to just run swaps on this thing in a liquidity pool. How many swaps per second can I get? And if we take all the throttles off, we're finding somewhere on the order of 1,000 plus. Now we did a bunch of performance, speculative performance work that got that even higher, substantially higher. But just in terms of what we could do today, just take the throttles off, we could do like 1,000 TPS, 1,000 swaps per second, which is a huge number. You should go check out what the performance of a bunch of other chains are. 1,000 swaps per second is very good. And there's a lot of things that we can do to improve this, but let's say 1,000 swaps per second. Okay, good. And how much gas per second does that turn out to be? Turns out to be somewhere between 150 to 300 million gas per second. So in real world utility, we could see somewhere around a 10x improvement on gas per second on the network, if we just had a solution to this problem of we throttle by gas per second, but gas is a crude measure of what is actually safe on the network. Okay, so that's the background, and that's the whole story behind this hit. Instead of using gas for throttling, we will make our own measurement. So let me switch to a different guy here. So this is a very high level view on the consensus node. So what happens is a user submits a transaction, any type of transaction to the network. And the first thing we do is we on a particular node. So they submit it to a particular node, and the first thing that we do is we do pre-check. And in pre-check, we do a variety of things. One thing is that we check to make sure that the payer exists, that the transaction was signed by the payer, and that the payer has sufficient funds for that transaction. We do all those sorts of checks up front. There's other checks that we do as well, but that's like a principal one. But another check that we do is we check the throttle and we say, okay, do I have enough capacity to accept this transaction into the network? And the way that it works is that we've got, of all the nodes in the network, 32 nodes, each node gets an even share of the throttle capacity. So if we say 10K TPS, it means that each node gets, 1/32 of 10K TPS. That's what they each individually get. So each node is doing its own pre-check. It looks at it and it says, do I have enough throttle space for this? Now, our throttles also have like a bursting capacity to it. It like it's smoothed out over, depending on the throttle bucket, 10 seconds, 15 seconds, 3 seconds, whatever, depending on which type of thing it is. But we have some kind of pre-check that we do there where we check the throttle. We refer to this as the front end throttle or the ingest throttle. We use the same term for the same for the same place where we check that throttle. Now, once it's past that, if it passes pre-check, we go to gossip. Gossip goes to all the other consensus nodes in the network. And it also, each transaction that it receives ends up going into the hash graph as part of an event. In that, the events get sorted, we get consensus, and then it creates a round. So in each round, we have a bunch of events. Each event has a bunch of transactions. Those get passed to the execution. Execution then is going to check throttles, and these are called our backend throttles. Oops, I forgot my little guy there. There we go. Backend throttles. We also fire up the EVM and do all the transaction handling, staking rewards, fees, all that kind of stuff happens here. Execution then creates blocks, which then get sent out to block nodes and mirror nodes. Okay. So the key point is that there's two different throttles. There's a front end throttle and there's a back end throttle. And this is why it matters. If you're a user and you submit a transaction to the front here, if your transaction is going to be throttled, you would like it to be throttled here because you don't pay for that transaction. The transaction gets submitted and you go, well, I guess I hit a throttle. Too bad. I'll try again later. No charge. If your transaction were to go through this whole system and come back to execution and get throttled, you still have to pay for a portion of that transaction. And the reason is that if that were not the case, then an attacker could just raise or wait for the network to become busy or raise the level of work on the network to the point where the backend throttles would be busy, and then they could just send an infinite number of transactions in here that would all fail on this backend throttle, and the whole network would have been doing all of this work. It's sticking things in blocks that are stored forever, and it's doing all of that for free. That would be bad. So the general rule is that if your transaction stops at pre-check, you don't get charged. If your transaction goes to gossip, you will be charged. You'll be charged enough to cover the cost of the bandwidth that the network used to gossip. You'll be charged to cover the cost of basic consensus and basic execution, and to store the thing inside of a block and export it. Turns out about the price of a crypto transfer, right? Because we do all that stuff in a crypto transfer, so that's about your minimum price. So that's why the difference between front end and back end is important. Okay, for normal transactions like a crypto transfer, this is easy because we all know every consensus node knows what its share of the throttle bucket is. When something comes in, it can do the pre-check. Life is good. You're going to get charged here. In fact, we don't even run that back end throttle for the user transaction. There's a little longer story there, but you're not going to get charged for crypto transfer on the back end. It's just going to find out on the front end and throw it away. EVM is a different story. We have no way of knowing at the time that we hit the pre-check whether or not you are going to end up getting throttled on the back end because, of course, the amount of gas that's used by a smart contract is totally a function of the amount of work that you are doing, right? And who knows what it is? I don't know. Execute your call. There's state, there's opcodes. We execute them, then we figure out how much gas it is. Even if you were to pre-run the contract, that's no guarantee that that's what's going to happen when you get to the back end, because when you pre-run the contract, there's certain state that you're executing with. Meanwhile, this is an asynchronous system. There's a whole pile of other transactions that are already being gossiped, already going through consensus, already being executed, and they could change the state of your smart contract so that by the time your contract call actually got its turn to execute for real, state could be different in that contract. The amount of gas you use could be different. So there's just no way to be able to properly throttle on the front end. And that's actually what we ended up creating the backend throttle for in the first place, was for the EVM. So there is always a possibility, and this is unique to us relative to Ethereum. There's the possibility that you will pay for a contract call, even though your contract wasn't actually executed. It'll be a low cost, but it's a real cost. So that's just something to keep in mind, is that with smart contracts, there's no way for us to perfectly pre-check it and apply the throttle. So it just has to go through the system. And if it turns out that the system is super busy, you will pay for a smart contract call, a little, crypto transfer worth. But even if it wasn't your fault, right? And that's honestly, that's sort of unfortunate. I wish that there was a great solution to that. I haven't found one. The way that Ethereum avoids it is by not having fair ordering, right? The rule on assembling the block is that you do pre-execute those transactions, and then you know exactly how much gas they use, and then you know how what you can stick into a block. But the only way that that can work is if you're able to reorder the items. So the non-fair ordering makes it work well for that. Whereas in our case, fair ordering, Hashgraph has no idea how much gas that thing's going to use either. Now, in order to try to smooth this out a bit, what we did is we created this rule that said if you submit an EVM transaction, so every EVM transaction has a gas limit associated with it. Like you, the user, say how much your gas, the maximum gas is you're willing to pay for this thing. And that's a nice little, helper for you as the user, because that way, if your transaction somehow, runs wild, you can still get it terminated without paying an arm and a leg. You can say, what's my max? Sometimes we call it max gas, but it's technically the gas limit for this transaction. Now, what we did was we said, okay, we will do as much pre-checking as we can do. This is what we do today. We'll do as much pre-checking as we can do. What we'll do is when you send us a transaction, we'll look at the gas limit and we'll say, can I let that through my throttles? And if I can, I let it through. But because a bad guy could say, I'm going to use 15 million gas, but then actually only use 20,000 gas on the back end, they could exhaust your throttles and not allow anybody else to run any smart contract calls for a very low price, because they just do the minimum, because if you charged them based on the minimum. That's why we came up with this 80% rule, which is totally incompatible with any other Ethereum network. It's our own invention, but the way that it works is that we say, well, if you tell me you're going to use 10 million gas, then by the time we get to execution, I'm either going to charge you for the gas that you used, or I'm going to charge you for 80% of that 10 million, which would be 8 million gas, one way or the other. That's what you're going to get charged. And it's unfortunate because it's always a little squishy in terms of how much gas you're going to use. And so people just set their gas limit to be artificially high based on what they're willing to pay. And it goes through the thing, and then they pay 80% of it, even if they didn't use hardly any of it. And we see this all the time because when you're doing your gas measuring, it's like sometimes it's 200,000 gas, sometimes it's 300,000 gas, sometimes it's 400,000 gas, and you don't want this thing to fail. So you just set it to 500,000 gas, and then you just suck up the cost. And there's two problems with that. One, well, you as the developer user, you're getting charged more than what you actually use. And the second thing is um, uh, we actually end up doing less work per second than we could do because again, people are using more of that gas throttle. They're paying for it, but they're using more of it that they need, which is sort of unfortunate. We don't get as much work per second that we could get. Okay. All that as background. What this hit proposes is that we eliminate the gas per second throttle entirely. We won't use it on the front end. We won't use it on the back end. We just get rid of it entirely. Instead, what we do is we create a new table of values that are based on actual measurement. We do this approach that I mentioned where we run a particular opcode or system contract to precompile essentially in a tight loop, measure its wall clock time, measure the number of times that we executed that thing. And once we have that number, that gives us some idea of what our gas per second is. We measure it on representative hardware, which is what we do for all the other throttles that we have, like our 10K TPS throttle, all these throttles. We benchmark it on representative hardware. We figure out what the numbers are. We pick a conservative value, and then with some buffer and padding, and we say, okay, that is going to be the operational cost or ops costs for this opcode precompile or system contract call. Now that we have a more accurate value that tells us how much that thing is actually worth, then we set a throttle based on that instead of gas per second. And then because there is no way to pre-check that on the front end, we just remove the front end check for EVM entirely, and we just do the ops throttle on the back end. And this is what's meant by precise smart contract throttling. Instead of this crude gas measurement, we'll do it by what we actually measure the cost of these things are. And then when we get to execution, that's where we'll do the throttling. Now, under normal circumstances, what we should see, number one, that 80% charge that we do disappears. So we become more Ethereum compatible. People can they can set the gas limit up to whatever the maximum configured for the network is per transaction, which currently we would probably on Hedera, I mean, it's outside of Hiero, but probably Hedera would leave it at 15 million. Maybe Hedera raises it to 30 million. There's a proposal in Ethereum to have a gas limit per transaction of 30 million gas, I think. So, we'll pick some number. Hedera will pick some number for that thing, but there will be some configured limit per transaction. So no one transaction is going to show up and say, I'm going to use 15 million, 150 million gas or 30 million gas. There will be some limit. So even if people were using 15 million gas, it passes through all these things. We go to execute, we start executing. They can use however many, all up into that 15 million gas, and then their transaction concludes. And maybe that 15 million gas used, 300,000 op cost, maybe it used 30 million op cost, who knows? Since those two things are sort of decoupled from each other. And again, we will charge based on gas, exactly like we do today, but we'll throttle on the back end based on the actual ops costs. So what we would anticipate is, again, that 80% charge goes away. So anybody who's using smart contract calls today will be happy with that. The second thing is that because our capacity is so much larger for executing smart contracts than what we are able to do today, the likelihood in the near term, at least, that we encounter these backend throttles is not very high. So, and the reason is because there's just not, I mean, 300 million gas per second or 150 million gas per second is a very big number. And so you'd have to have really high load in order to exhaust that. So for a while, nobody will ever see any sort of throttling happen on the back end at all. And then, of course, we're always working on improving our performance to try to get that number higher and higher. And then we'll have sharding and all the other things in order to scale that load out. But we should be aware as a TSC in this feature, there is a point where when the network becomes sufficiently saturated, smart contracts will start being throttled on the back end. And if that happens, then there is some cost to your contract being throttled, and you have to submit again. Fortunately, the price is very low. So again, it's like the cost of a crypto transfer, basically. So what that would mean is like if your typical smart contract invocation was, say, somewhere between 2 and 5 cents, and a failed one was, 0.0001 cent dollars, then you're just looking at a fraction of what would be the overall cost. So retry isn't super expensive. It's not like gonna blow up your business. It's irritating because you have to see what happened and then say, "Oh, fine, submit a new one, try it again." But it's not the end of the world. So that's the long and the short of it. Um, we remove the 80% thing and become more like Ethereum compatible, fewer differences that developers have to know about. We still have the backend throttle, which is no different than today, so that problem still exists. We are able to run way more gas per second. If you were thinking about the sustainability of the network, for example, on Hedera, then you could say, all right, how much is gas? For those who don't know, gas is currently priced at 0.70852. That's how many USD per gas. So if you were looking at what if we actually executed 150 million gas per second, that'd be somewhere around 12 and a half cents, 12.78 cents per second, 86,400 seconds per day. That would be 1.1 million per day, 365 days. You get the point. That's good revenue, which is good for the sustainability of the network. So I think this particular feature is really exciting to me. It unlocks way more on-chain computation. It gets us closer to Ethereum compatibility. It unlocks performance at least an order of magnitude higher than what we can do today. It unlocks use cases that we couldn't do today. DeFi use cases, which currently would be limited at maybe, based on the normal gas that they use, they would normally be limited to somewhere around 60 TPS today. They'd be able to go up into the hundreds and hundreds of TPSs, even like normal swaps at 1,000. Those sorts of things become reasonable. And yeah, it's a little bit irritating if you're the network owner and you have to figure out what's the cost for each one of these opcodes because you have to have representative hardware, you have to run all these tests on them to figure out what the values are. But that's the work that we do for Hedera at Hashgraph, so we'll take care of all that. But at the sort of architecture level, this allows us to really unlock the capabilities of the system far beyond what we're able to do today. That's all I got to say on it. Any questions or thoughts or concerns?
Hey, Richard. In terms of the actual calculation of the new unit measure to replace gas, the ops per second.
Yeah, the ops cost.
I'm sorry.
Ops cost is what we're
Yeah,
calling it.
the op cost there. Where is that being measured in real time to replace gas? And is that something that over time, once we, demonstrate its utility, does that go then contributed back to Besu?
Right. So it would not get contributed back to base, so I'll go backwards on that, only because Ethereum has no need for this ops cost. It doesn't factor in anywhere there. So the way that Besu works is that they have there's this class that represents the EVM. and it's non-final, which worked out good for us because we were able to subclass it. And in that subclass, we added in our own. It's a pretty small class, so we're not talking about a huge delta from EVM. It was actually very minor amount of changes that we had to make to this in order to make it work. Basically, what they do is they have a method that in a loop takes an opcode, does a switch on it, invokes the opcode, updates gas. And what we did was we just inserted into this the ability to do our ops code check as well. So it essentially we're metering two things. We're metering gas and we're metering ops costs. That has to be done carefully in order to keep the performance up. Because now you're doing, two different meters instead of one. There is a cost to it. But it wasn't like a huge delta to base. It's very small, and we didn't have to change the core basic classes at all. So
As a result, you're outputting those two metrics simultaneously out of the EVM
yeah,
as implemented in Hedera.
yep,
And then using, since you're doing both, but we're getting rid of the throttle for the gas limit throttle, that is the second one just used to ease the transition to
it's
ops
for
cost?
charging. So we charge based on the amount of gas you use, but we throttle based on the actual limit of what we can do, the ops cost.
And then what's the correlation there? I mean, it's obviously if it were 1-to-1, then you wouldn't need both, right?
Yep.
But if it's variable, then that's why you need both, one for charging
That's
and
right.
one for throttling.
That's right. And the reason that we have to charge on gas, so the other option would be that we just didn't do the ops cost at all. We just kept using gas. But what we did was we said we created our own gas schedule. So we could say, yeah, Ethereum says it's 3 gas per opcode, but for us it's 1 gas per opcode. And Ethereum says it's 20,000 gas for that, but it's actually only 1,500 gas for us, and so on and so forth. We could do that, but there's a big problem with that from a compatibility perspective. If you're a smart contract developer and you create smart contracts, you are using your development tool chain, which often includes always includes other tools outside of Hedera. And that tool chain is going to estimate how much gas you're going to use. And then you would run it on Hedera, and it would be like wildly different, the amount of gas you used. And that would break all kinds of people. So we have no choice but to use gas, the official Ethereum gas schedule for the whatever particular hard fork we're on, as the gas schedule for our network. We have to charge on that. But it turns out that that works in our favor because our ops cost will allow us to do lots of gas per second, and we get to charge for that. So we get to charge that. Milan.
Yeah, hey Richard. First of all, I'm lower my hand. Yeah, I think it's an excellent direction with this because I as you also mentioned, like one of the issues has been like estimating gas, and also the estimation of doing so could vary widely, and then then mostly the decision that will be made is like, okay, we'll estimate it just higher because what does it matter, right? I mean, it's still the costs are low, but that would also mean that we would reserve like a lot of gas, which could then be utilized normally if we don't have that 80%, could utilize for other smart contract executions or other network services, obviously. So I really love this, really I love this direction. For example, I remember had some discussions with some people about this 50 million gas limit, which is currently the gas throttle, if I remember correctly, on the Hedera network, 15 million gas per second. And just checking, for example, and maybe my estimates, maybe that's already adjusted, but I remember like Bonzo and SaucerSwap both had about around 1 million gas that was used, and I think the estimation was just below 1 million gas. which will then in turn gives you not a lot of TPS, obviously.
Yeah.
So yeah, I think this is an excellent direction, and I'll have another deep look on the hip. Also, my question was like, if we're going a different, we're adjusting this, then how will it work in terms of like a reservation of other network services, or like if there's a lot of smart contract executions within a second, is there like one preference over another, or is it yeah, how does it work? Maybe just for me, maybe I've missed it somewhere else that I can read up to, but just that I kind of get how that will work.
Yeah, you bet. So, yeah, no, it totally makes sense. So what we did, and again, this is like, okay, Hiero hat off, Hedera hat on. So what we did for configuring the Hedera network, because any network could take the Hiero configurations and they can tweak how they do this. But the way that we did it on Hedera was that we said we're going to reserve half of the second for sort of smart contracts. And that way, if the smart contract was completely loaded with the worst case attack possible, we would still have half a second available to do all the other normal transactions. And the smart contracts and other transactions, they do share some throttle buckets. So like if you were to execute one of the smart contracts, it takes away some of the 10,000 TPS that's available for people and so forth. So it all kind of balances out. Now, what we have done in our just, amongst all of us friends on this publicly recorded video is that we set up our performance networks and we run 15 million gas per second and 10K TPS simultaneously. So we know that we're able to have both of those things run flat out today. What I would expect us to do for Hedera is the same thing when we get to ops per second. We will choose ops costs for these things such that we can run that throttle flat out and still do all of our normal crypto transfers and everything else. That's kind of what I'm anticipating.
Excellent. And I imagine this will also feed right into the Hiero hooks, that those become more predictable as well, because those are they're more sizable as function as well.
Exactly. In fact, I really wanted to get this hip out before hooks so that we could really unlock it. Because, hooks are interesting, but if you're limited to, 300 TPS for hooks, then any accounts that are using hooks are not going to be able to have very much TPS. Maybe they don't need it, but aggregate, if a lot of people were using hooks, it'd bring down the overall TPS of the network. If you put this thing in place, then that's no longer an issue, and you'll be able to run, a high number of basic crypto transfers with hooks. It should still be in good shape.
Excellent. Well, great work. I'll be diving more into it, but thank you for the presentation, and definitely great direction.
Yep, you bet. Keith.
Yeah, thanks, Richard. That was a great presentation. Just from a docs perspective, what do EVM developers need to know about this, if anything? I mean, is the message to EVM developers just, use the appropriate amount of gas, you'll be charged for gas. Is there anything else we need to be telling them?
Yeah, so we have it down here in the how to teach this section. So definitely we would want to let them know that there's no more of this 80% minimum charge. Of course, even if you don't tell them that, they will just be pleasantly surprised and everything will be great because they'll get charged less. But that's a good sort of thing that we can share with people. This is the main thing that they have to really be concerned about. We have to make sure that it's documented that when the network is under load, your transaction can fail with a specific error that indicates that it was throttled, and it'll cost you this little amount. You just have to resubmit your transaction. That's the main thing that they have to be aware of. Outside of that, the other two things are, again, it's like performance gains. It's like, well, this is all just good. And we'll also want to publish what the ops costs are so that people will be able to look at it and get some idea of what their um, what impact they have on the throttle system. But honestly, I don't think anybody's going to pay too much attention to that part. I think it's pretty much going to be hey, everything's faster. And they go, yay, everything costs you less. Yay. And oh, by the way, you have to deal with this. Boo. But okay, it's no different than today. So I think that's basically the story. Alex.
Yeah, I was just curious whether there's a future, and I'm raising things just for consideration for including capabilities that would maybe offer us opportunities in the future. And what I'm getting at is we talk about having EVM or Ethereum compatibility, which obviously is important. But if there's an option to indicate that I don't need to be quote unquote Ethereum compatible, just as in the invocation of the contract saying that, yeah, no, I'm going to go just do everything native op cost, not do gas, et cetera, that I indicate in my contract that this is not, Ethereum compatible, or however we want to indicate it, that this is, say, Hedera tuned, whatever nomenclature we want to use, and potentially remove our need to do any sort of gas calculations, just do everything natively up cost for that contract, and potentially even gain some more efficiencies and performance.
Yeah,
So like V1 versus V2, right, or something like that, as a header in the contract.
yeah, I think, I mean, I wouldn't preclude it and say that it could never happen. I don't think that we're close to that in terms of, the advantage that we have and the demand on the market side to be Ethereum compatible is really high. And the reason,
Sure,
like,
sure.
for example, we had a customer who, got a third-party contractor to work on all their stuff. That contractor never worked on Hedera before, but he knew EVM. And
Right,
so
right.
they're going to come and make everything work. But if you wanted to have a specific like native tune thing, there's a lot of things that we could change. In order to make it practical, there would be a big investment on tooling in order to replace a lot of the tooling that exists in the Ethereum world. So there'd be a lot into it, but it's certainly, not technically impossible. Something.
Yeah, no, the only reason I raise it is just thoughts of if there's any things that would be good to do now, just from a future proofing, even if it's not, if it's a kind of a dead end entry point that which might be more difficult to do if we try to do it later.
Yeah, I
If it
think,
doesn't matter, then that's
yeah.
we can dismiss that, but just a thought.
Yeah, as far as I know, we're not boxing ourselves in any corners there. We should be okay. Another thought, by the way, for those on the call, one of the things, and then we should probably go to the next tip. But one of the other things that I'm really interested in is this idea of developers running their own relay and enhancing the relay so that it has the ability to sign and submit transactions on behalf of the user. And this obviously wouldn't be used by a retail user who's using the system, but for, if you're like a saucer swap or a DEX or something like that, and you're sending the transactions, then having some kind of a backend like a relay that you run, that you host, or you have a third party host on your behalf that has a signing key. Advantage to that, in combination with block nodes, is that that relay could be watching the throughput of the system by just observing the block stream. And it could anticipate what the network load looks like and make all kinds of decisions. Like, should I submit my transaction now? Should I wait to submit my transaction? Do I submit my transaction, and if it fails, I create and submit a new one automatically? There are ways of making the sort of the developer pain that I talked about with execution kind of go away, and the probability of running a transaction that doesn't work get reduced, or not, depending on, because you may say, I want to wait for the network to quiet down before I run my transaction, or you may say, dude, I'm going to compete for my transaction to be executed, and I'm willing to pay for a few throttled transactions in order to get mine in. You can make those sorts of decisions, maybe encode it in a relay, and that way every developer in the world doesn't have to do all of that work themselves, write all that logic. We can bundle it up in something like the JSON RPC relay, have people run their own relay, and then it handles all these. So there are other things like that. Alex, that we can do in order to make this really smooth for users as well.
Right, right, right.
Cool.
Okay, cool.
All right, I think we should jump to the next HIP, which let me bring it up, is the generally smart contract. So this is a really cool one. Let me pull that guy out and share that screen. This one's relatively straightforward, and super powerful. So this one comes from Little Tarzan and Michael Tinker. And the idea was we have scheduled transactions. We would like two things. One is I would like, we want our scheduled transactions to be able to call smart contracts. That's great. But the really cool thing is give a contract the ability to create scheduled transactions. So this involves adding a new system contract that would allow the smart contract service to schedule future smart contract calls in that smart contract service. And the idea that you could have a contract sort of invoke another contract has some really interesting powers and abilities. So there's a few of them that are here listed in user stories, rebalancing of DeFi positions, vesting claims, DAO automation. Um, you could even imagine a like a DeFi system that is like, I'm going to do a certain number of or any type of smart contract where it's like, I have a big backlog of work. I need to do like a million things. I can't do a million things in a single contract call. So I'll do 10 things and then I'll schedule another call into myself. Do 10 things, schedule a call into myself. Do 10 things and sort of give you this ability to really write, autonomous smart contracts, if you will. And there's no other network that we're aware of that's doing something like this. It's really a very special capability that we would be exposing that would unlock totally new use cases that you can't do on any other network that we're aware of. So the system contract API is defined here. You have a chance to go and review this and check it out. But essentially, you're able to schedule a call and delete a schedule. And there's this call here is interesting. So as with everything, there need to be throttles and stuff to prevent a smart contract from, say, using up all the available capacity of the system. And also to prevent any other transactions coming from the outside world of being executed. We don't want any, no matter how many smart contracts are using this feature, we don't want to make it so that they can, edge out all the normal contracts from being able to execute or all the normal transactions from being able to execute. So what we do with scheduled services today is that there's a certain number of transactions per second that we allow you to schedule. And basically, you can think of it as like a bucket for each second. We don't actually create a bucket for every second, but you can say virtually there's a bucket for every second. And there's a certain capacity for that second. And so you can, if there's capacity in there, you can put your transaction in it. Otherwise, it's in the following second. And we don't make a guarantee that that actual wall clock second is when this thing's going to execute, because, of course, consensus time and wall clock time might be separate from each other. But we just say that on or after that second in consensus time, we'll execute your your transaction as best we can. So we have some basically limit to how many you can do per second. And this call allows you to check whether there's room in that second. So basically, the contract can do various smart things. It can have some logic that says, hey, is there room in that second? Because I would like to execute in that second. Yes, there is. Okay, I'm going to schedule my call in that second. Or it could say, is there room in that second? No, there's not room in that second. Okay, try the next second. Nope, no room. Try the next one. No room. And it can have a loop and it can try every single one. Or it could have logic that said, okay, try that second. No, that second's not available. Okay, try the next second. No, that one's not available. Okay, try a power of 2 farther seconds. Okay, try farther. So it can do back off. It just depends on the logic of the transaction. Or it could also say, I'm going to check the next 5 seconds for my optimal second. If none of them are available, then forget about it. I won't schedule a call. All of that is available to the smart contract. It can decide exactly what policy it wants to use by using this has scheduled capacity, figure out, is that a second that I am going to schedule? Do I want to schedule it? What can I do? And then it can call the scheduled call. And of course, each one of these things will have an ops cost associated with it as well, assuming that the other HIP passes and some gas associated, or sorry, yeah, a gas cost associated with each one of these different calls. And then you have these other variants here that allow you to specify, who the sender is going to be. So in a smart contract call, you have the sender, who's the sender, and you can specify who the sender is going to be. Is it going to be the contract? Is it going to be the person who called this contract? Whatever. And then you also have this execute call on sender signature option, which is, when I'm going to schedule this transaction, but it doesn't execute unless it's been, like normal scheduled transactions, unless it gets signed by a third party. And if it gets signed by a third party, then we'll go ahead and execute the call. So anyway, just a few variants of what these methods are. You can dig into this to understand better those details, and then there's some little examples, but it's a fairly small HIP. The primary point here is just that from inside of a contract, you can schedule your contract or another contract to be invoked, and you can use a sort of arbitrary policy for what to do if the second that you're trying to schedule for is busy. And you can sort of hunt for the second that you want using whatever your approach is, and then schedule your contract call. And that's this HIP. If no questions, then that's what we got. Michael, you asked, are these diagrams published anywhere? No, of course not. Just made it up this morning. But I was thinking of trying to put that into the HIP. So we'll at least have that diagram in the HIP. We do have a number of architecture diagrams that we need to document. But
Yeah, I would definitely throw those in the HIP. Those are great.
yeah, it's very helpful for understanding how it works. Okay, so that's it. Back over to you.
Good. Thanks for all those introductions. So let me share the agenda again. So the next point we have on the roadmap is the initial backward compatibility guideline, which are that you created as a pull request for the governance doc. And this is especially to ask people one more time to have a look at that and review it so that we as a TSC can vote on that one in the near future. Do you want to give again a short overview about what it contains, Richard?
Boy, it's the Richard show today. Okay, so we did a whole session on this one a couple weeks ago.
Yeah.
So
Exactly.
I think a question that I more had, I think it's also in that discussion thread is what is, and I think we mentioned also, we touched upon it lightly last week, is where do we place these documents? Like, is there, in a way I thought, is this, perhaps maybe I'm totally wrong, is this like is this a process type HIP? Or, I was still kind of trying to figure out where could we place it, how do we make sure that's actionable?
So my feeling was that this sort of thing is more in line with the charter than in line with sort of the HIPs. And so the home for this thing was in the governance repo where the charter lives. Because this is like governance related as opposed to say a feature on the network or a way of using the network. So my feeling was that this would be more of a governance doc that went in this.
Okay. And so is it an idea as well to together with that maybe to have like a subfolder that we have similar documents like that we create that becomes more structured, that is like, I don't know how you would call it, but a guidelines folder or
Yeah.
something.
Or a policy folder or something like
Yeah,
that.
yeah. We should start with something like that. I agree on that, Megan. So currently it's all in the root. Maybe start with like, oh, there are guidelines, and start put it in the guidelines folder and maybe have them in the README MD listed as the first step. All of that. Would that be good enough as an initial step? Oh, Alex has hands up.
Oh yeah, no, but I think it's something along the lines of Emil is asking around this being a normative document, in so much that we're expecting this to be applicable to all the projects under Hiero, and if so, what is the oversight expectation around oversight and enforcement? Meaning, even if we don't do it proactively, if, say, from a community perspective, things get raised, oh, there's a breaking change in Project X, it didn't follow these guidelines, is there an expectation that we it takes any sort of action associated with that? So I know that as you're highlighting there, it's currently scoped to these particular repos, but it potentially could go expand further. But the point being is that what is then the reaction of the TSC if there's a breaking change or that does not conform with because we talk about a guidelines, but the language in here says must, right? And it is inheriting those words that are very prescriptive.
Yeah, I think that's the intent of it, is that if these particular projects, and maybe we end up expanding this someday so that any of our mature projects fall under the same kind of guidelines. If they're not behaving according to these policies, then we would need to have a discussion with those maintainers, because that is the role of the TSC, is to provide that sort of technical oversight for these projects, and part of that technical oversight is compatibility. So we would have responsibility to provide oversight and make sure that these projects are behaving correctly in that way. And the reason that's important is because in general, we don't want the TSC to be too bossy, right? We want the maintainers of these projects to be able to maintain their projects. But I think this is one of those places where the integrity of the entire Hiero project, it can be undermined by there are certain maintainer behaviors that can undermine the integrity of the entire Hiero project experiment. And some of those would be if maintainers are acting unethically, or if they are not listening to the other maintainers, and there's an inter-maintainer fight. All that kind of stuff could happen. But also, I think breaking a policy like this could really undermine the rest of our project. So it's important to
Oh,
to
no disagreement. It was just trying to understand from a TSC perspective if there is deemed to be or escalated some sort of violation, however we want to term it, of these principles or these items that we say must, right? And how do we even determine that? For example, when it says all changes must be evaluated, okay, how do we know that that was done if it's a must?
So Richard, do you want to say something?
I was just going to say, in that particular case, I think all we do is we just define the policy, and then that's what they have to do. And if they don't do it, then we have a conversation with them. I don't think that we need them to fill out reports or anything, because reports can be fabricated or whatever. It doesn't significantly advance us. And I want to avoid any sort of heavy-handed, sort of process. It's really just we lay down the expectation, and then they abide by the expectation. And if it turns out that they didn't, then we have a conversation with them. That's the way that I see it.
Yeah, and I would add, so from my point of view, the big picture comes together when we have, for example, defined like what are graduated projects for us, what are incubating projects and things like that, right? Because then we could say something like, okay, those routes are a must or really defined for projects in graduated state. And
Right.
if a project that is in graduated state, like don't care and always, do breaking changes, then we as a TSC need to, or it's a must then, to move it back to incubation. That is my point of view here. And then it would not even be this list, then it would be like all projects in the graduated state need to follow those rules. If you break those rules, I mean, if you break them you can talk, right? But if you don't care and break them often, then you need to go back to incubation. That would be my point of view here.
Yeah, yeah. Again, it's just understanding what expectations there are with this or similar documents, and just to clarify that when we say guidelines are generally, hey, we think this is a good practice. If you follow it, great. If you don't, no big deal, right? But if it's a standard or a practice or a policy or no a procedure, then that has a different sort of weight and a different set of obligations on the TSC to ensure that the projects under its authority are are compliant, or at least there's a mechanism to affect that compliance, either proactively or reactively.
Yeah.
So it's just clarifying, look, when we're creating these these documents, these again, whether they're guidelines, policies, what have you, that we have one consistency so that the community knows how to interpret that and what to expect from the TSC.
Yeah. So I think we, in the same folder or in the same org, we now have those guidelines regarding what is a committer, what is a maintainer, how is the voting of all that work. And I believe we matched 90% maybe on how the reality is, right? And that's why I like to call it guideline, because maybe in, I don't know, some months we come back and say, oh, Jessica has now introduced this great voting mechanism for GitHub. So now we change our guideline and say, hey, please do it with that. And if then a project for the first 3 months still do it in the, like old way of doing it, I think it's fine. That's why I would call it guideline, and if we really see everything works and everything is great, then we can say, yeah, that's now a must. That is now the baseline of what needs to be done. But I don't like to directly start with that on day one, because
That's a fair point. I mean, I think
yeah.
that's a good way of looking at it, that this is the practice we want to see across the code base. Let's deploy this as a statement of intent, as a guideline, but then say revisit it in 6 months or whatever period of time to say, if we're seeing that these practices are being followed, adopted, then we can maybe elevate it to say that this is more normative.
Yeah, agree on that. I think that is good. Okay, we already way over time. Since some people of the TSC are still here, I would like to open one link for 1 minute. So I started an issue where I tried to correct, like, oh, is there a typo in the charter, or is there something that maybe need to change? Because if we do this charter change, and if we find additional small things, we should correct and do everything in once. So if you have something you think should be changed, I share the link here. Please add it to this issue so that we have a a point where we can correct all those things. I assume Megan is quite good in that. Should I
Yeah.
record it?
Yeah, that also reminds me that probably that's maybe for next week's agenda for the election in September, that we're really square on that, because the charter, is a little
Yeah.
bit taken up on that piece.
Yeah, exactly. There's even like the TSC chair that we need to do. I found like something that might be changed there too. But I agree, we should move that topic forward too. Yeah. Jessica.
Yep, so I posted another one that we have pending review. I brought that up with the legal team. They approved the changes, and all we need to do is go ahead and submit this change. But before we do that, I noticed that we have the charter in both the Hiero repo and the governance repo. So do we need to get rid of one?
Yeah, this one is what Richard did, and he did it on the Hiero repo and not on the government repo. So what we should do, where I agree with you, is we should link it, but I think we should not just merge this pull request.
Okay, so should we do a similar pull request in the other one? I can go ahead and create it if you guys want.
Yeah, that would be fine, and then we can correct here and check if we want to do all of that in once or do it in multiple.
I think for the extra changes that you have there, I might need to, just for reassurance, I might need to go again to the legal team, but they've been pretty fast at responding. Well, this time
That
they
is,
were.
and that is great. So Jessica, the idea here was the legal team is slow, so let's correct and just go once to them. If you already got approval from the legal team for the other things, we shouldn't wait and move that forward.
Okay, so I should just copy the pull request into the right repo.
Yeah,
And
yeah.
I'm gonna remove the linking Hiero, but link to the governance one.
Yeah.
Okay, sounds good.
Perfect.
Thank you.
Okay, thank you. So I think, Jessica, we should switch to the next meeting. Otherwise, people think it won't happen, right?
Okay. Thank you, everybody. Thank you.
Thank you all. See you. Bye.
Bye-bye.